And I guess without further ado, let me introduce Van Eden. Van is a physicist. He spent most of his career working on surface physics, so the physics of surfaces of materials for the likes of IBM research and Microsoft research, and also in academia. And when the dengue fever outbreak hit, he said, geez, we should do something about that. And so he's been investigating mosquito traps and mosquitoes, and I'll let him tell you about it.
Okay. Thank you very much. So how many of you have a scientific background? About half of you. That's great. And are any of you kind of actively practicing scientists? Again, like 4, 5, 6? Pardon?
Engineers.
Engineers. Well, that counts. Okay. So I know we have at least one entomologist in the room. Do we have any others? Chris at the back. By the way, that's Chris. He's just started Department of Health. Yeah. So great. That kind of helps me get an idea of who's here. So I got into this because when the outbreak happened, of course, everybody's asking questions on the internet, you know, what's going on? And I started looking into what other countries do. And given my background as a scientist, I kind of turned pretty much straight away to the literature, the research literature, to find out what other countries were doing. And very rapidly, you find them talking about integrated vector control. And a component of that is community involvement. And a big part of that is breeding site eradication. And another part of that is trapping. And you begin to read statistics like 2004 Thursday Island off the coast of Queensland in Australia. They had an outbreak, and their response was to deploy 4 lethal ovitraps, they're called mosquito traps, 4 traps around every house within 100 meters, I think it was, of every case that appeared. And they wrote in their paper that within 4 weeks, about 90% of the Aedes aegypti were gone, that they had eliminated, and that the dengue outbreak was over. So that's pretty impressive stuff. So that got me interested in it. The issue that I ran into was that these traps were, you know, you couldn't go to the hardware store and buy one or the garden store and buy one. So I thought, wow, this is not rocket science. We should be able to figure out how to do it with easy to obtain materials from the local hardware store. So that's what I set out to do, kind of reverse engineer the traps that were being used and designed by entities like the CDC in Puerto Rico and the Australians, Queensland, and various other places. So I thought I'd begin. Let's hope the pointer works. Doesn't, unfortunately. Yeah, okay. Too far. This was the first mosquito to arrive in Hawaii over almost 200 years ago. It's the house mosquito. I pity the. Could you dim the lights? It's generally brown, kind of plain, not terribly interesting looking, but it carries avian malaria, so it's very hard on the bird population. Carries West Nile virus, so Japanese encephalitis, I believe. So it's pretty bad. Come on. Can you advance it one? Oh, wait, I got it. The next one to arrive was Aedes aegypti. And this is the yellow fever mosquito. And you can see there are characteristics that are important for its identification. You can see, for instance, the knees have white, all of its elbows are white. And it has this very nice harp-shaped curve on the side of its back. And that's very characteristic of this mosquito, and it's how we identify it. And you can see this when you catch one. I guess if you have 20-year-old eyes, you can see it with your eyes. But you need. I use a hand lens, and it's really very obvious when you catch one. About a decade later, Albopictus arrived. Albopictus, you can see the bright white stripe down the back, the middle of the back. and that's its characteristic identifying feature. Albopictus is a better competitor than is Aegypti, and so when they're both in an environment that they're both adapted to, in general, Albopictus will displace the Aegypti, and that's what we've observed, and it's been observed in many countries. So those are the three mosquitoes. We're going to ignore the Culex, the very first one, because it doesn't carry dengue, and I want to focus on these two. Part of the reason is because there are characteristics of these two that make it relatively easy for us to trap. So I want to dig into those characteristics a little bit more. So first of all, these are anthropophilic mosquitoes, meaning they like people. They like to feed off people. And a very important difference between Albopictus and Aegypti is that Albopictus is quite happy to bite your cat or dog. There's this research paper, Faraji, I think that's a CDC paper, shows that half their blood meals come from domestic pets. What that means is that Aegypti, because it focuses on people, is really the dangerous one, because it's not going to bite a dengue-infected person and then become infectious itself, and then bite lots of other people. The Albopictus is going to bite a lot of cats and dogs, which can't get dengue. So that's a good thing. Aegypti will just keep biting people. The next thing is the Aegypti are very well adapted to living indoors. Right? They're endophilic. They will come into your house. They will hide under your bed. They will come out of your closet and bite you when you're not aware of them. So that's something that makes them very effective as vectors of a disease like dengue. Albopictus is more feral. It lives outdoors more. And so therefore it's, again, not quite as bad of a vector as Aegypti is. And their behavior... So I want to skip down to breeding in containers. So breeding in containers, both of them breed in containers, but the Aegypti are really focused on man-made containers like the discarded rubbish that people have. And what that means is that the Aegypti really prefers living in a very populated area, an urban environment. And so if you look like in Puerto Rico, the center of San Juan or whatever it is will be an Aegypti location. Out in the suburbs, it's more an Albopictus domain. They do better when there's more vegetation around. Now, one of the survival advantages that mosquitoes have evolved is the ability for their eggs to survive dry. And when they're laying their eggs in a container, unlike the Culex mosquito, they do not lay their eggs on top of the water. Instead, they lay their eggs on the side of the wall. Now, the rationale for that, if that's the right word, at least the only thing that I can think of, is that both of these mosquitoes need to have water in that container for a minimum of about 2 weeks, or the larvae will die, because it takes 2 weeks to go from an egg to an adult. And if it doesn't have water that whole time, it's going to die. So, if you just lay your egg on the water, there's a chance it might evaporate. If you lay your egg on the wall, then that will only get submerged if it's just rained. So it makes sense. So that's one of their survival techniques. And in fact, Aegypti here has a great advantage over Albopictus because its eggs can be viable for as long as a year. So it can survive a drought very, very well. Albopictus, we're looking at 5 weeks or so. So think about it. We just went through a 10-week drought after Christmas, big, long drought. That was probably really hard on the Albopictus population, at least on the Puna side that I'm familiar with. And the rains that came may well have been advantageous for the Aegypti. I don't know. I'm hypothesizing, but you can imagine it. Now, the last 2 points, both of them prefer rough walls when they're laying their eggs, because they lay their egg on the wall. They don't want it to just fall into the water. They want to wait till it rains. So they are looking for a rough wall where the egg won't fall off. And so that will give us a design criteria for our traps, and you'll see that in a moment. Then the last thing, this thing called skip oviposition, is important enough that I want to dedicate a slide to it. So when a female feeds, it gets a blood meal, or actually in this case, both these mosquitoes will actually take many blood meals before they collect enough blood to be able to lay eggs. They'll go through, the females will go through these cycles where they're getting blood meals until they're ready to lay the eggs, and then when they're ready, they start visiting multiple places to lay eggs, and that's called skip oviposition. And you can see they go through about 5 of these cycles in a lifetime. Each one of those cycles, they might visit a dozen or more egg-laying sites. Okay, now here's where it gets really interesting. There's a thing called the extrinsic incubation period for dengue virus in a mosquito. When a mosquito bites a person who's viremic with dengue, and the mosquito gets the dengue virus in it, it takes about 12 days for that virus to replicate and then make its way into the salivary gland of the mosquito, where the mosquito can inject it into the next person. So there's 12 days there. That's 2 cycles, right? So that means that mosquito is going to be visiting 20 or 30 places where we can trap it and kill it, right? And really break the cycle that way. However, if there's thousands of breeding sites around, because of all the trash we leave in our yards, then the probability that she'll go into one of our traps is lowered. So clearly, breeding site elimination is really important for the success of the traps. Okay, I can't remember what the next slide is. Did it? Let's see. Okay, thank you. This is very old. Here are some quotes from 3 research papers. And I'm not going to read them to you because you can probably read them yourselves. But essentially what they're saying is that using these traps is very effective. The classic requirement is 3 to 4 traps per house. That is a recommendation from the World Health Authority and the World Health Organization and numerous other entities. That's just their standard. And you can see that they're saying prevents outbreaks of Aegypti. Well, you can read it. I don't need to read it for you. But basically, what it's saying is that these have the ability to do what we want, which is to reduce the population, like that Thursday Island example I gave you before. All right. So I already mentioned that I wanted to make something that was easy to make, use common chemicals, is relatively safe, and I'll talk a little bit about the safety as we go. And if you want, this is not a workshop I'm giving here for how to make a trap. I give those as well, but I'm just going to gloss over how we make traps, but you'll get the idea. The important thing is all the traps have these 3 things in common. The smooth walls on the inside, because they don't like to lay their eggs on smooth walls. Instead, we give them what I call a landing strip, or a landing pad, and we put an insecticide on it. And one such that when they land on it, within about 10 or 15 seconds, they'll have a dose that will probably kill them. The third thing is you need to have something that attracts them into your trap. And in this case, is water. The mosquitoes are looking for water, and preferably water that's a little bit, that has bacteria growing in it, because the larvae feed off of bacteria. That's their food source. So if there's no bacteria in it, then they'll have nothing to eat. And the females can tell that. So they're very selective about where they lay their eggs. Okay, do they work? They do. In my experience, when I first put them out as a test, it was remarkable how quickly they took effect. We live in an area where we're bordered on 2 sides by jungle, and where we're used to, the mosquito dance when you're outside. And that went away within a couple of weeks. And so essentially what I did was I put traps around all the houses in my neighborhood, well, 4 houses in this little cul-de-sac that we live on. And all of us watch the population go down. Many other people have had that experience as well. Happy to give you references if you need them. But I always want to give a caveat. These are not going to wipe out the mosquito population. First of all, we're designing lethal ovid traps, which means that the female that we're trying to catch has already had a blood meal. In fact, she's probably had several. And only after that can she lay the egg. So it's not going to get rid of the mosquitoes that have, for instance, just hatched. The other thing is, we all live in neighborhoods, or we all live in an environment that may contain what I call mosquito factories, like a poorly maintained catchment tank. That's a great one for Hawaii. Bromeliads, a bank of bromeliads, beautiful, but each one of those bromeliads could be producing 2, 3, 4, 5 mosquitoes per day, and when you have 100 plants there, you're looking at a really big population of mosquitoes getting created. You probably all can't read it as it gets to the bottom. The traps also do not target the Culex mosquitoes. Remember the very first slide I showed with the brown mosquitoes? Very common house mosquito. They're not interested in it, so they won't go in it. It won't affect them. But they don't carry dengue, so maybe that's okay. And then the last point is that populations rise and fall. That's just part of the way nature works. And so sometimes there are going to be mosquitoes around no matter what you do. But the end story is that these things are effective. They're based on research done in many parts of the world where it's been shown effective, where it has become a standard part of the response of the health authorities there. Okay, so now I'm going to show you a really basic trap. It's a jar, right? It's a pickle jar. A pickle jar that's been spray painted black. If you don't want to spray paint it, wrap it in plastic. But spray paint is great. And pardon? Only on the outside. If you put it on the inside, you make it rough. And that's not what we want. So we all know glass is smooth. So what we're going to do is we're going to have a landing pad made out of very heavy paper. This is construction paper that you buy at the hardware store that is good for about a month in water before it disintegrates. Or you can use a stick like this, simple stick. And we're going to use a couple of very common chemicals. So this is a taro ant dust. It contains a pyrethroid called deltamethrin. And so there's a plant called chrysanthemums that make pyrethrins that are insecticides. That's a man-made version of it. It's a fairly low concentration, and what we do when we make the trap is we moisten the landing pad, put a little water on it, and then you sprinkle the ant dust on it, kind of like you're dusting a donut, not too much, hopefully, and you wipe it on to smooth it around, do both sides, and that will be what you leave in your jar for the mosquito to land on. Then in terms of the water bath, we're going to half fill this. So that's about a quart of water. And in the water, we use something that we're all used to probably, which is roach powder. Roach powder is boric acid. There's research out of Pakistan that shows that this is very effective at a concentration of it turns out to be 1 milligram per 100 milliliters. And that turns out to be, in a quart like that, you'd put roughly a heaped teaspoon. So you put a heaped teaspoon in here, dissolve it, put your stick in, and that's your trap. As simple as that. You can make it a little more attractive to the females if you drop a small amount of compost in it, or grass or leaves or something like that, because that helps improve the bacterial growth. So that's, I think it's all written there, so I can move on.
Is that ready to go right then, or does that ferment a while?
Nope, it's ready to go right then. Yeah. Okay, so version number 2. Oh, I should mention about the toxicity. Yeah, actually, there's a question at the back.
It said deltamethrin, and then it said
So the question was, what's the difference between deltamethrin and the ant dust? Yes, those are, I should have spoken more clearly. You sprinkle the ant dust, which contains the deltamethrin. Sure.
How long is it good for?
Oh, thank you. This is good for, this trap, the design is good for about 4 weeks. So in terms of toxicity, there was a teenage girl in Florida, I believe, who ate something like 5 grams of the deltamethrin, not this stuff, but the active ingredient. This is only 0.05% or some small amount. So she would have to eat 10 of these to get that dose. She recovered in 48 hours. And so it's really not that bad. And of course,
Pets.
beg your pardon?
How about for pets?
Pets should, okay, so the researchers, many other researchers have used deltamethrin and they address that. And basically, on a stick like this, you'll have approximately about, the goal is to have 0.1 milligrams per square centimeter. And you can see that's probably 200 square centimeters. So you're looking at 2 milligrams. So to get a significant dose, the dog or cat would have to eat 20 or 30 or maybe thousands of these. I don't know. I can't do the math in my head that fast. But basically, the conclusion they reached was that it wasn't possible for an animal to eat enough and drink enough of the liquid to get a dose that would harm them. Yes, question.
Where would you suggest putting these around your property?
So trap location, I'll get to that in a minute. Thank you.
What makes it stick? What makes the powder stick to the stick?
What makes the powder stick to the stick? Basically, it adheres. It's just a powder. It's held on by
You get it wet first.
static, basically.
Stick wet. Oh, you get
Yeah,
the stick wet.
you get the stick wet,
Oh, okay.
and the stick will dry out. But interestingly, when the stick is in the water or the paper, you get capillary action that wicks up and helps keep it damp, which is one thing the mosquitoes are probably looking for. Okay. The so-called four-mouth trap. The problem with the 4-week trap is people get kind of bored of having to make it again every 4 weeks. I mean, it's not that bad, but still, people want them to last longer. And so I continued reading the literature and I found that bifenthrin, which is another pyrethroid, is more stable than deltamethrin. And there was research done, Williams, 2007, I think those are Australians, that bifenthrin, they made things like this that were, they measured them after 4 weeks in the field and found no decrease in their effectiveness. So I have extrapolated that. If there was no difference in 4 weeks, I've said, well, okay, maybe we can go 3 or 4 times that long. And so I kind of described this as my 4-month trap. Now, in terms of the larvicide, I also propose using one called spinosad, which if you're an organic gardener, you'll probably know it. You can use it on your plants up to the day before you harvest. And it was shown in another research paper to be effective for more than 20 weeks. So that combination, and in this case, because it's such a long-lived trap, I made it bigger. I thought it should be bigger because the biggest problem with traps is they dry out. So if you start with just a quart, it's going to dry out much too soon. So instead, you switch to a smooth-walled 5-gallon bucket. This is, I think, maybe a 3-gallon bucket. And in this case, with a lid, the Australians did a whole bunch of work on what's the right dimensions for a trap. And they basically came up with something that was about a 5-gallon bucket with a lid with an about roughly 6-inch hole. And so that is your trap, the trap body. The reason this is a little more complicated is because bifenthrin, you buy it in a concentrated form, 10% concentration, or 8%, I forget, 8%. And you have to dilute it down to the right concentration so that when you paint it on, you get to that magical 0.1 milligrams per square centimeter. If you have too much, then it can act as a repellent to the mosquitoes. If you get too little, it may not kill them. So there's a little bit of It's not very hard. It's just basically some dilution by a specific amount. And by the way, they're pink because I put red food coloring in. That way you can tell which end has got the poison on it. So when you make these, you end up wanting to make hundreds at a time. So you can say I'm making hundreds at a time, which is a lot of hassle for an individual who only needs 4. So that's why I encourage communities. Like in my area, Seaview was one of the first communities to start doing this, and they were making them by the hundreds. Now, in terms of toxicity, bifenthrin is relatively non-toxic to humans. You can use it in food preparation areas. When the stick is dry, you can handle it without really having to worry about it. Obviously, I'm going to wash my hands before I eat. Yes, question at the back?
How do you know you're putting 0.1 milligram on?
So the question was, how do I know I'm putting 0.1 milligrams on? Basically, you do the math. So you take a stick and you paint it, you weigh it on a very accurate scale. You paint it with water, and you measure how much of that water is on the stick, right? So say we got 1 gram of water on a stick, to make it easy to do the calculation. We know that we want to have 0.1 milligrams per square centimeter, and we know that the area of that stick, let's say this stick, this is probably about 100 centimeters squared. So 100 centimeters squared, 1 gram of water. You just do the math to figure out the concentration of the solution that you need, so that when you paint it, all that's left is 0.1 milligrams of the active ingredient per square centimeter. It's not hard. It's on my website if you want to see more details. But basically, your question is very valid. How do you calibrate what you're doing? And that's really what you do. So for instance, if you're not able to get the bifenthrin, I used one called Bifen, and there's another one called Tallstar. They both have a specific concentration. It's roughly 8%. If you can only find one that's 3%, then you have to redo the math to figure out how to paint it on, or how to dilute it before you can paint it on. First, we'll talk about maintenance. Maintenance is pretty obvious. Don't let it dry out. Don't let it get filled with stuff that shouldn't be there. It is not necessarily a bad thing if there are dead things floating around in it, like a dead snail, frog. One of the worst mosquito factories I've ever seen was a 5-gallon bucket full of dead snails. It was just frothing with larvae like boiling rice. It was horrible. Remake it. Don't bother trying to reuse any of the parts. Just remake it when you go. In terms of disposal, put the deltamethrin strips, put them in the garbage. And the other stuff you can tip onto the ground because it's just boric acid and spinosad. They're fine. So now the location. Really recommend people have a map. If you're going to have more than 4, then please make a map because you will forget them. And if you forget them and leave them in the rain, they just become mosquito factories. And we don't want that to happen. Shade is very important because mosquitoes want to get out of the shade, out of the sun, because it dries them out and they die. Likewise, the wind. They're looking for dampness, so vegetation is really important. The mosquitoes will happily come out and bite you and go back into the bushes 30 feet away and just repeat that over and over and over. Egypti, because they like to get indoors, they like to hide by your front door so that they can get in when you go in. So those are good places for traps. Particularly the Egypti, after it's bitten you and it's coming out to find an egg-laying place, if it finds one right at the front door, it's going to be happy. Also, you can put these indoors. If you don't have good screens or whatever, then it's perfectly reasonable to have these indoors. If you're worried about cats and dogs getting in, put chicken wire over them. Really, this is a relatively simple technology, and you can use your imagination or think carefully about the issue that you have and figure it out. All right. Any questions on the mosquito traps before I move on?
Well,
Hi.
we have a lot of bromeliads. Would you say
Yes.
Egypti is not so much that, it's only the other mosquito that goes in there?
Okay, I don't want to be misleading. So the question was, what about bromeliads and Egypti? My understanding is that the albopictus are much more feral and much more interested in, much more able to live in plant containers. That does not mean that Egypti won't. Okay, so bromeliads are really an issue for Hawaii, and a lot of people are very defensive about it. In fact, I've gotten almost into a fight with somebody. I don't mean a physical fight. I'm just like an argument with someone because they love their bromeliads, and they have a 8-foot by 60-foot patch of bromeliads right next to the mailboxes. Yes, so that's an issue that Hawaii has to face. We have enough beautiful plants that we can remove many of the bromeliads we have without missing them. Question?
What's your opinion of using BT to control mosquito larvae?
So the question is, what's my opinion of BT? BT is an excellent way to control larvae. So BT is a Bacillus thuringiensis. It's another organic treatment. Typically, you use it, you spray your tomatoes to stop the caterpillars eating them. Again, you can probably use it up to the day before you harvest your food. It works very well, but the problem with BT is that it needs to be refreshed approximately every 2 weeks, depending upon the formulation. For bromeliads, there are other things you can do. BT is probably your best option. There are other things, such as a thing called methoprene, which is an insect growth regulator that you can sprinkle in them. But yeah, bromeliads, we need to be cautious. Yes?
How about just soapy water?
Questions about soapy water. Department of Health recommended using soapy water. I believe the CDC told them to stop recommending that. It doesn't work. The amount of soap required to kill a larvae is about 10%, if my memory serves. So 1 cup of water, a tenth of it, you can figure it out, right? 10% solution of soapy water is not really something you're going to want to have around. And then when it rains, you have to do it again. So the question is whether organic pyrethrins are effective. I can only assume they will be, but I haven't read anything about it because it just hasn't come on my radar. But I would imagine that they are. I don't know about their durability in the environment, or in other words, how often you'd have to repeat it. Yes, Chris.
Natural pyrethrin should work, but they do break down very quickly in UV sunlight. So within a day, they've dissipated.
Within 1 day.
Yeah, within a day's exposure of sunlight, 90% of it's gone, more than 90%.
Okay, I'll just repeat that. So Chris, who's the entomologist from the DOH, says that within a day, 90%, a day of sunlight exposure, 90% of the natural pyrethrins are destroyed. Yes, question.
So mosquitoes can't actually breed in just like big leaves that are laying on the ground because there's not really enough moisture that's going to hold there for the 2 weeks of waiting for the eggs to mature. So it's not likely they just hide in those in that
okay.
climate.
So the question is can the mosquitoes breed in leaf material that's laying on the ground, because it doesn't typically hold water for the 2-week period required for the full progression of the egg to an adult. And I think, yes, that's correct. However,
they sure like to hide there because when you walk through them, there's...
Yeah, sure. That comment is specifically about the Aedes species, right? The yellow fever and the Asian tiger mosquito. It's not necessarily true of other species. Like the Culex may be much more adaptable. There are lots more mosquitoes than that as well. So when you're walking through the forest and the mosquitoes are coming up, those may or may not be the dengue carrying mosquitoes.
But they can breed in just a couple of teaspoons of water, right? In a very small amount.
Yeah.
That
So
that's in a cap or
so
a child's toy that's laying outside.
yeah. So indeed, you're correct that they can breed in a very small amount of water. The issue is whether that water will dry out or not. So if it's rainy, and it's raining every day, yeah, in a little cap from a discarded water bottle, they can breed. So every little piece of trash we have out there can support a breeding site if the conditions are correct.
It must be there for 2 weeks.
Must have water in there for about 2 weeks. You have to have time to get the egg in the water, to go through the stages into an adult, and then hatch.
And the oil on the top of water in the bromeliads, does that, until it rains, but is that effective? Because
so-
if there's larvae...
So the question about oil, when you cover the surface of a water body with oil, the mosquitoes are not able to breathe through it, and so they suffocate. I can imagine that would work for bromeliads if you want to spray cooking oil or something on your bromeliads. But again, you have to make sure that you're getting into all of the bromeliads, and that the rain will break it up, as you pointed out. Yes.
I gather your traps probably aren't going to be effective around a large bunch of bromeliads. It's not going to make enough difference to make any difference. Is that right? Or?
So using the traps, so in effect, if I can restate your question, will the traps work near a mosquito factory like a bed of bromeliads? The answer, I think, is probably not. Because there are so many other places where they can go to lay their egg, the probability of finding your trap is very low. One of the more interesting places I found mosquito larvae was I had cut off a papaya at about waist height, and it had filled with water. You know, papaya trunks are hollow. It had filled with water and was a really, really good breeding ground for mosquitoes. Just, again, boiling with larvae.
We were always told to put a can over the top of any, when you cut off a papaya.
Put a can over the top.
Put a
That's a
can
great
over
idea. Yeah. Okay. Just one more question, and then I'm going to move on.
Some of the commercial mosquito traps utilize attractants such as
Yes.
octanol or carbon dioxide.
Yeah.
Could we make use of that to trap around mosquito factories?
Okay, so the question is, some commercial traps use attractants, chemical attractants, to attract the mosquitoes to the trap. And can we use that? Those attractants are primarily focused on mosquitoes that are not yet ready to lay eggs, right? So they're looking for a warm body to bite, and so those attractants are typically things that the mosquitoes associate with dinner, right? The traps that we're making are at the other end. It's after she's already had all her blood meals and she's ready to lay eggs. The attractant in the traps that we use here is the water itself. They can detect the water. They can detect the chemicals in the water. The natural chemicals in the water. They can detect the bacteria. They can tell if there's other larvae in the water. They are very sophisticated.